This is only for a zeroth order reaction. All right, so let's look at how to go from a differentiated rate law, which is at the very top, to an integrated rate law. And I say this is optional material. Oh, I don't know why I put it twice. Okay, so how would I go about integrating that equation at the very top? You want to do a separation of variables? Okay, and you can then write minus dA is equal to k sub 0 dt. And now I'm going to integrate this. And if I integrate this, what do I get? I get A. Okay, but we have to integrate from 0. Sorry, this is going to be A sub 0 here to A. This is going to be 0 to T. So this is going to be A minus A naught is equal to minus KT.
Oh, is this also only for 0?
Yeah, this is only for zeroth order reaction. Right? And if I rewrite that equation, oh, yeah, I get this equation. So this is the integrated rate law for a zeroth order reaction. So if I now want to plot the concentration versus time, what will this graph look like? Again, we're talking only about a zeroth order reaction. What will the concentration as a function of time look like?
It'll be linear going down.
It'll be linear going down because this here is y equals mx plus b.
Why is it A minus A naught?
Because of the limits a sub 0 and a.
Then why does it say the concentration of A equals A sub 0 minus
I just moved this over onto the other side.
So you're going from T naught to A.
Rachel?
Oh yeah, sorry.
Okay. So the slope of the straight line is negative k. Lauren?
So the concentration is the concentration of the reactants.
Right. Okay, let's look at a first order reaction. So A going to P, A is the reactant, P is the product. What will the differentiated rate law look like? Minus dA dt is equal to K times A to the power 1 minus K times A to the power 1. Okay, so here is a plot of rate versus concentration. Yes, Angela.
Oh, sorry, just to repeat. So it's negative K?
Oh, sorry, I didn't mean to say that. It's K to the power of A. The negative is out here. Yeah, did I say it wrong first?
Can you really just repeat that?
Okay.
You just write it.
Okay, that's the first order reaction. Differentiated rate law for the first order reaction. So you can look at this and say if we're plotting the rate as a function of concentration, you're going to get a straight line whose slope is going to be the rate constant. if you take this equation, this differentiated rate law, and integrate it, you're going to get this integrated rate law. And I hope you take some time to do this at your leisure. But again, this is not required of you. How you go from this equation to this equation, you don't need to know, but you can figure it out if you've taken calculus. This is the integrated rate law, which can be written either in terms of natural logs or in terms of exponentials. So what plot should I make that is going to be similar to this plot here? This is for a zeroth order reaction. I plotted concentration versus time and I got a straight line. What do I need to plot to get a straight line for a first order reaction? Oh. What do I plot for the straight line? What's on the y-axis? Tiffany?
Log of A.
Log of A. And on the x-axis? Time. And the slope here is going to be minus k. Right?
Oh, yeah.
Okay, this is just y equals mx plus b. What would you get if you plotted the concentration versus time for a first order reaction? Not a straight line. And if you plot concentration versus time, what will it look like? Exponential decay. Okay? That's this here. All right, let's look at a second order reaction. A plus A going to P. Here is the differentiated rate law. Okay, to be consistent with what I said before, I would have to put a 1/2 here, but I'm going to omit that. Consistent with every other textbook. So I'm being incorrect here, but I'm being consistent with other textbooks. It's not a big deal. It's just a factor of 2. Okay, if you integrate the second order rate law, you end up with dA over A squared. If you remember your integrations, this is the integrated rate law for a second order reaction. Remember, a differentiated rate law tells you how the rate depends on concentration. How does the rate depend on concentration? An integrated rate law tells you how the concentration depends on time. That's always true. So if you want to get a straight line here, you plot on the y-axis 1 over the concentration, and on the x-axis you plot time, and you get a straight line for a second order reaction. Questions? Okay. How do we determine these rate laws? As I said before, the goal is to obtain K, X, and Y. K is the rate constant, X is the order with respect to A, Y is the order with respect to B. We're going to talk about different methods. The first one is called the method of initial rates. And I'm going to illustrate it with an example. What you're doing here is trying to figure out K, X, and Y for this reaction here. And what you're doing is you're doing 4 experiments, but you're doing the 4 experiments with different initial concentrations, and you're measuring the initial rate. So 4 initial concentrations corresponding to 4 different initial rates. This is all the information that you need to figure out K, X, and Y. Actually, in this case, it's going to be K, X, Y, and Z, because there are 3 reactants here. Okay? So I'm going to illustrate just how to calculate X, and then I'm going to ask you to figure out how to calculate K, Y, and Z at your leisure before you look at the notes that I will post on. So let's see, how do you determine the rate with respect to the bromate ion? Okay, I want to know, so I'm going to say that this is A, this is B, and this is C. So the exponent here is X, exponent here is Y, and the exponent here is Z. So I'm trying to figure out what X is. So I look at experiment 1 and 2, and I see that when I double the bromate concentration, what happens to the rate? Doubles. Therefore, the rate of this reaction is K to the power bromate to the power 1. Because when you double the concentration, the rate doubles. Supposing when you double the concentration, the rate became 8 times larger. What would the exponent be? 3. When you double the concentration, wait, is that, yeah. When you double the concentration, if the rate becomes 8 times larger, then the exponent here would be 3.
How do you get 3?
It's 2 to the power 3 is 8. 2 to the power 1 is 2. That's why we can say when you double the concentration, if the rate doubles, the exponent is 1. When I double the concentration, if the rate quadruples, then the exponent is 2. Okay? So using similar arguments, you can fill in the blanks and figure out what Y is, what Z is, and also figure out what K is. Questions? Alice? Oh, you should figure that out, okay? One thing I can say is that the rate always has units of concentration divided by time. Okay, because rate is this. So always rate has to have concentration divided by time as the units. But the rate constant will have units that depend on the value of X, Y, and Z. And I'll ask you to figure that out at your leisure. All right, the second method is based on graphical methods. So we measure the concentration as a function of time. and we plot different functions of concentration versus time. So let's go back to, this is an example of a zeroth order reaction. To get a straight line, we plotted concentration versus time. For a first order reaction, what did we have to plot on the y-axis versus time? The natural log of concentration versus time. For a second order reaction, what did we have to plot on the y-axis? 1 over the concentration versus time. So you try these 3 different possibilities, and whichever gives you a straight line is going to be the right rate law. So can you take a moment here and figure out what is the rate law for this reaction? Can you talk to your neighbor for a couple of minutes, or a minute here?
Yeah, that's the first order.
What did you say?
So in one voice, this is a second order reaction. Okay? So the third method is to measure the half-life. Supposing you had 64 molecules, you want to know how much time it takes for the 64 molecules to become 32. How much time does it take for the 32 molecules to become 16? How much time does it take for the 16 molecules to become 8, and so on? That's what I mean by half-life. The half-life depends on concentration in a manner that tells you what the rate law is. If the time it takes for 64 to become 32, 32 to become 16, 16 to become 8, 8 to become 4, 4 to become 2, if the time for each of these processes is the same, it is a first order reaction. We talked extensively about first order reactions at the beginning of the semester. Nuclear decay. Nuclear decays are first order processes. This is the basis for being able to do carbon-14 dating, because it takes the same amount of time for the material to become half its original value, irrespective of the initial amount of the material. But that's true only for a first order process. It's not true for a zeroth order process. It's not true for a second order process. And you can prove that. And what you will find is that the half-life for a zeroth order reaction depends on the initial concentration. For a zeroth order reaction. For a first order reaction, it is independent of initial concentration. And I'm going to omit the proof here. I hope you will take a few minutes and fill in the blanks and prove this equation is true. Okay, before you look at the answer in my notes. So the first order process, the half-life concept is very nicely illustrated here. The amount of time it takes for you to go from here to here is the same as the amount of time it takes to go from here to here. the half-life is independent of the initial concentration. This is true only for a first order process. So here are some examples of half-lives. Radioactive decay of uranium-238, 1 billion years. Here is a reaction whose half-life is less than a microsecond. And finally, the method that you're going to use in lab is called the method of reagents in excess. So supposing you have a reaction A plus B going to product, and the differentiated rate law is this. You don't know that. But if you were to use a huge amount of B, then what you would do is to make the concentration of B remain constant during the course of a reaction. So you artificially make this reaction into a first order reaction, even though it is really a second order reaction. So by using an excess amount of B, we make the concentration of B a constant, and take that constant and lump it to with this K here, and we have now a new differentiated rate law, and this is called a pseudo first order reaction. Pseudo means you have manipulated, it's a false first order reaction. This is the true reaction kinetics, but you've manipulated in such a way that you have simplified the problem, and now you can determine K observed, the new rate constant, and from that you can determine the kinetics of the process. You can do the same thing and switch it and make A, B in excess, and then the rate will only depend on B. So you can artificially manipulate these complex situations and make them into pseudo first order reactions. And that's what you're going to be doing in lab. So let's summarize what we've talked about today. We've talked about zeroth order, first order, and second order reactions. We've talked about differentiated rate laws. For the zeroth order reaction, the rate depends on concentration to the power 0. For a first order, rate depends on concentration to the power 1. And for a second order, the rate depends on concentration to the power 2. The integrated rate law you obtain by taking the differentiated rate law and integrating it. This is what you get, and this is what you get. Now, you always want to get a straight line, because that makes the analysis easy. So to get a straight line for a zeroth order reaction, you just plot A versus T, but that's because of this equation here. This is y equals mx plus b. So to get a straight line, you plot A versus T. To get a straight line here, you plot log of A versus T. For this, you plot 1 over A versus T. How do you get K? Remember, what we are really after is K, X, and Y. How do we get K? We look at the slope of this straight line, and that gives you K. Same here. If you measure the half-life, the relationship between half-life and concentration is different for each of these 3 different processes. We will stop here, and I will see you guys bright and early on Monday at 8:30. But between now and